All right, so what you see on the screen is basically what we're going to be doing for the next 2 weeks. So we're going to be discussing each one of these reactions in detail, and then we're also going to be discussing them in the context of application, like what do we use it for? And again, I don't want you to ever lose sight of why any of this is important, right? You think about if you're a biology major, a chem major, or whatever, animal science, it doesn't matter. Um, all of these reactions have a application somewhere within the scope of your discipline, right? Whether it's a pharmaceutical application, whether it's a biochemical application, all of these things are a part of, like, the grand scheme of, you know science, right? So all of the things that we learn how to make, and the different types of reactions we learn about, substitutions, elimination, making double bonds, and reacting them, converting them, and doing cyclizations. When you think about, just think about from a pharmaceutical perspective, or from a drug perspective, right? All of those reactions have a place somewhere in there in the synthesis of, you know, different compounds, uh, so on and so forth. So don't lose sight of that. I know we kind of zoomed in looking at the reactions, and it's almost like looking at a painting, but just zooming in on one pixel of color. But you always have to have that grand overview as well. So don't think we're just spinning our wheels. All right, so we're gonna look at the application part, like how to apply these different reactions, and we're gonna start out right here. Notice I have this broken down into quadrants. So we're gonna look at reactions of alcohols, and then conversions of alcohols to carbonyls, and then reactions of carbonyls, and then reactions of amines, which is another functional group that acts in a similar fashion as an alcohol. All right, so I'm gonna cut this top part out, and we're just gonna work through these quadrants. So let me do this. All right, so when we're talking about reactions of alcohols, these are three of the reactions that we are going to concern ourselves with. All right, transesterification, and then esterification, and then Williamson ether synthesis. Now, before you panic and think that it's something new, it's not. All of these reactions, if you have a decent grasp of nucleophiles and electrophiles, then this is not new. This is just application of what you already know. All right. So for transesterification, let's go there. You can see that if you take an alcohol, right, and a carboxylic acid, and then react them together in the presence of a mild acid and warm it up, that's what the delta is for, right? You can see you get an ester in the product, right? So you get an ester in the product. That's a very simple reaction. Can somebody tell me? I just want to see how you thinking. Can somebody tell me, for a reaction like this, you can see that the OH group here got swapped out for this part of the alcohol. What type of reaction is that? If I have a carbonyl and I want to add a nucleophile to it, what kind of reaction is that?
Is that substitution?
I'm glad you said that. So it looks like substitution, right? It looks like you swapped which we did. We swapped out the OH on the carboxylic acid for the alkoxy group. That's this part right here of the alcohol, right? The alk for the chain, and the oxy for the oxygen.
So would it be what we just did, the diet, oh wait, hold on. We just did it. Oh, hold on.
Are you talking about when we were doing organometallics?
Yeah, when we were doing like the acylation and the alkylation.
It's not quite close, but not quite. So let's think about this. All right, let me give you a rule of thumb. If you have an sp2 hybridized carbon, which is what this carbon and the carbonyl is, the C and the C double bond O is sp2 hybridized, right? You can't do substitution there. What you can do is addition and then elimination. Right. So if you remember back to when we did conversions of alcohols to alkyl halides, there was one of the reagents, thionyl chloride, was similar. It was an addition to thionyl chloride followed by elimination, and then we kicked off a chlorine, and that became our nucleophile. So all of these carbonyl reactions, both of these right here that you see right here, both of them are going to be addition elimination reactions. So you add first and then you eliminate. So let's look at the mechanism for that reaction. Right. And thank you for your input. I value that because anytime you get feedback or input, it opens up a discussion. So that's good. So we're going to take that reaction. I'm just going to redraw it. Right, so this is my carboxylic acid. First step is addition. Right, if you remember from part 1, when we talked about the different types of reactions, addition was one of them. And addition happens on pi systems, right? So we have a pi bond, like a carbonyl or a carbon-carbon double bond or a triple bond or something like that. You can do addition to those pi systems. All right, so we're going to take alcohol here. We're going to attack the carbonyl, right? I'm not attacking the OH because it's already electron rich, but that carbonyl, again, all of this is stuff from part 1. There's a dipole here. That governs the reactivity. So it's that carbon that reacts because of the dipole. All right, when I do that, when I add to the pi bond, I also have to, break the carbon oxygen pi bond when I add to that carbon. Otherwise, that carbon is going to have too many bonds to it, right? So after the addition step, we get to an intermediate, which looks like this. So this is OH. This is O minus. This is R, and then this is, we'll change the color on that. O. And then this is positive. Right, so this intermediate is common to carbonyl addition. Anytime you add a nucleophile to a carbonyl, you're going to get to an intermediate like that looks like this. And I think we talked about this when we were doing gradient additions to carbonyls. Am I right?
Yes.
Right, so anytime you add a file to a carbonyl, you get a tetrahedral intermediate, and that is going to decompose to give you your product. All right, so we got another step here. So I think one of our side products is water. You can see that right here. So we need to lose water, right? So this is in a sense a dehydration. All right. So how can we make water in this molecule? How can I turn?
Could you break that OH bond?
You can do a proton transfer, right? Is that right?
Yeah.
Internal, intramolecular proton transfer. So I can take this pair of electrons and do that. Give those back to oxygen. So now this is a hydronium. All right. Now, if I wanted to lose water, this was the addition step right here. And then this was a proton transfer step. What can I do to get rid of water?
Is this where our elimination step comes in or not yet?
No, this is it. So I want to reform the pi bond and I want to lose water. How can I do that?
So you would have to lose water, you have to break the hydrogen off, and then what is that called when you break the hydrogen off and then you create that double bond back?
We want to break the whole water molecule. We want the whole thing to leave.
Oh, okay.
Yeah, we want to break that CO bond, but then we want to make this CO pi bond, right? So it's the electrons from the oxygen, right, that are going to be used to reform the pi bond. And then we'll lose water at the same time. So this is the elimination step. Right. So then I end up with my carboxylic acid that looks like this. Well, this is R. And this is the alcohol that I added in. Let me change the color up here too. All right, questions about that? Again, if you have a working knowledge of part one, then a lot of this stuff is just application. That's why we spent, I know for those of you who took my class, that's why we spent so much time talking about nucleophiles and electrophiles and arrow pushing and dipoles and all of that stuff, because at some point we're going to have to apply it. All right, let's look at the next reaction then, because it's similar to this, but it's not the same. All right, so we're gonna, let me add a page in. We're gonna take the acid chloride now. This in this particular case, this is just, you can just do this without any heating or anything. It's the acid chloride is so reactive that you don't need a catalyst. You don't need to heat this up, nothing. All right, so let's look at that. So let me just cut that out. Oh, God, down here already. So this again is also an esterification. You got the same culprits. The only difference is now you have alcohol, and then you have an acid chloride, which is which is an analog of a carboxylic acid. So the first step is the same. I'm going to attack the carbonyl, just like I did in the previous reaction, right? I'm going to attack here. I'm going to break that CO pi bond. The addition step in all of these reactions is the same, right? It doesn't matter what you add to that carbonyl. When you do the addition step, it's going to be the same. You attack the carbonyl carbon and you break the CO pi bond. Like so. All right. What is that intermediate going to look like?
Wouldn't it be the same as the last one? You're attaching that oxygen to the
That's negative. Is that right? And then you got your R group here. Chlorine. Chlorine here, and then your alcohol here. So this is my tetrahedral intermediate for this reaction, right? What do I need to do next? All right, I'm not losing water as a leaving group, but I need to get rid of chlorine. How can I do that? How did I get rid of water in the previous reaction?
you did the proton transfer.
No, that was to make water. How did I get rid of it?
Oh, you did elimination.
Yes. So I need to eliminate chlorine. Right. So in reforming the pi bond, I'm able to do that. And I think on the handout, there's a typo. This should be HCl. So let me fight that out. Fix that in this handout, but I guess I didn't. All right. I can eliminate
This
chlorine.
was Shirley at the end.
That's going to give me this. All right. And then once I get you here, now we can do a proton transfer to get to the product, right? So the chlorine is just going to pick up that proton like that. All right, so then I'm left with my ester here. plus HCl. All right, any questions about that reaction? All right, it's a very similar mechanism to the mechanism that we saw up top. So again, when you're learning reactions, it's good to learn to classify them. Right, so we can put these two reactions in the same class based on how they work. Right, the mechanism is going to be very similar for both reactions. All right. The other reaction up top that's dealing with alcohols is the Williamson ether synthesis. Right, and again, a working knowledge of these functional groups is necessary. All right, so first thing you got to do is know what an ether is, and if you know what an ether is, then it makes the reaction less daunting because you understand what you're trying to do. You're trying to turn this alcohol right here into an ether. Right, so I'm going to cut this out, and then we're going to walk through this. This is a very basic mechanism. This is something, actually, we did this when we were studying nucleophiles and electrophiles in part 1, but we're going to walk through it. All right, so these are your reagents. You have an alcohol, you got an alkyl halide, and the presence of a base. You need a base. The base is there to deprotonate the alcohol. All right. So when you see this reaction, when you see this set of reagents, then you know that it's going to be an ether synthesis, a base, an alcohol, and an alkyl halide together. All right. So let's take let me show you how this works. So here's my base, and the purpose of the base, once it deprotonates the alcohol, is to make that oxygen a better nucleophile. Because now oxygen is going to be negative, right? And it's going to be plus that. All right. So this now is a better nucleophile. Remember, negative nucleophiles are always better than neutral nucleophiles. All right, so it's a better nucleophile. So now that can attack my alkyl halide. So I'm going to redraw it. And this is definitely all right. So what happens now? How can I show that? Because we've seen this before.
Don't you just break the CH3Cl bond?
Yeah. How do I do that though?
What is
That's
it?
a primary carbon, so it's not going to be spontaneous.
Right. I'm not sure. I can't remember right now.
I got a nucleophile in here with it, right? That can attack it. Right. That's the purpose of making the oxygen negative. So now this can attack here, and you lose the halogen. So this is where your alkyl halide comes in. Once you treat the alcohol with the base, stir it for a minute or two, and then come in and syringe in your alkyl halide. What type of reaction is this right here that I just illustrated? Right, now you can see that this is an ether, right? This is You got an oxygen with a carbon, single bond to carbon on both sides. What type of reaction is this though?
Is it SN2?
Yes, very good. It's the SN2 substitution, right? And that's why I said that we've seen this before, because this was one of our examples when we were looking at the SN2. This was an example that we did. All right. So as far as the alcohol reactions of alcohols are concerned, the three main reactions that we care about, and there are loads of reactions out there. It's not just these three, but these are the ones that we're focusing on. We have ester synthesis, which can happen two ways. You can do acid. You can use the acid chloride and an alcohol, or a carboxylic acid and an alcohol. And then we have ether synthesis, which we need an alcohol and a base and an alkyl halide. Right. And then the ether synthesis, 9 times out of 10 is going to be some type of SN2 type substitution. All right. Questions? Any questions? All right. So now let me pull up that grab that second quadrant, because we now see one way alcohols can react is to make esters or to make ethers. Now we're going to look at the other part of the quadrant, which is conversion of alcohols into carbonyls, right? These are what we call oxidation reactions. Right. So if you remember from GChem, when you learned about oxidation and reduction, it dealt with electrons, right? The loss of electrons is oxidation, the gain of electrons is reduction. But in organic, when you talk about something being oxidized, right, it's one or two things happening, or both, right? You increase number of bonds to oxygen, or decrease the number of bonds to hydrogen. Right? Both of those are considered what we call oxidation, and they can both happen at the same time, right? And most of your oxidation reactions, what you're doing is removing a hydrogen and also creating a carbon oxygen double bond. When you're talking about oxidizing up to a carbonyl. So I'm gonna go ahead and cut this out because I need to talk about how this happens. I'm not gonna talk about the mechanism in detail for these because can get a little convoluted with these different catalysts and things like that. But let me show you what has to happen in order to oxidize an alcohol up to a carbonyl. Right. So in order to oxidize this up, let me just give you a generic overview of what has to happen. So here's my alcohol. right? In the most generic terms possible, what happens is you lose H2, right? So you end up losing a hydrogen here and here, right? So that carbonyl proton, remember, I kind of talked about that when we were doing NMR. Right, you lose that and you lose the hydroxyl proton. So all of your oxidation catalysts do perform this in some type of way, right? So you lose the hydroxyl proton, you lose the carbonyl proton, some through some mechanism with each one of these types of reactions. All right. So then you end up with a carbonyl, and I'm going to put the H2 in quotes because you don't necessarily lose hydrogen gas, but you lose both of those hydrogens. Put that here. All right. So you don't necessarily lose H2, but it's just a way to think about it, right? Because I need to put that pi bond between carbon and oxygen in order to have that oxidized. All right. So up top, we got a few alcohols. We have let me change this to. I think I can. That's okay. I can fix it. So we can see that this is a primary alcohol. Down here is a secondary alcohol. I'll just write it in. And we also have a primary here. You cannot oxidize a tertiary alcohol. All right. Let me show you. This is a tertiary. I'll just use butanol as the. Why can't I oxidize this? Think about what I just showed you.
It's a tertiary alcohol.
Say that again.
It's a tertiary alcohol.
But why can't we oxidize it? You're right about that. It is tertiary. But why won't it oxidize? What am I lacking? Let me go back and show you. This is again, this is a generic alcohol oxidation mechanism. What am I lacking in a tertiary alcohol that would prevent this from happening?
Is it the hydrogen?
Which one?
Alpha hydrogen?
The carbonyl?
Yeah, that one.
Yeah, it's the carbonyl proton, right? If you look at a tertiary alcohol, this carbon does not have a hydrogen on it, right? So it doesn't have a carbonyl. Right? So that's why I can't oxidize it. In order for me to oxidize it, I need to be able to remove that hydrogen and the OH hydrogen. But the fact that that hydrogen doesn't exist in a tertiary alcohol means I can't do it. All right. So that's why over here, we're only looking at primary and secondary alcohols. So if you want to oxidize, and again, these are tools. It's like if you're building a house, you got a toolbox, you got a hammer in there, you might have a vice grip, you might have a tape measure, you might have a level, a carpenter's pencil. So all of these are just different tools that you use to get what you want. If I want to take a primary alcohol and turn it into an aldehyde, I got methods for that. One method is here, to use chromic acid, right? So if you see chromic acid in the presence of a primary alcohol, it's understood what's getting ready to happen. That is going to get converted into an aldehyde, right? I'm going to put a double bond right here. Right, I'm putting the double bond right there. That's understood because chromic acid is an oxidant. And what it does is it converts that alcohol into a carbonyl, right? So you can see right here, it's the same carbon. That's right here, same carbon. That's where your carbonyl is going to be, right? The other method for conversion of alcohols to carbonyls, or not the other method, but another method, is Swern oxidation. All right, I'm gonna make this into a bonus assignment for you to look this up. I want you to look up the reagents and the mechanism. All right, I'll make a link for you to submit it today. You got to turn it in today. So I want you to look up the reagents and the mechanism for Swern oxidation. This is by far the funkiest reaction I've ever done. And I'm not talking about funky in terms of like George Clinton funk. I mean, one of the byproducts is you get a sulfur side product, and it really stinks up like the whole lab. And all your dishes you have to wash and bleach in order to get rid of that sulfur smell. But you can tell when somebody's doing a Swern. But it's a very, very effective reaction. It's highly effective. It's very efficient too. You get really high percent yields, and very few like side products, and it's selective, right? So if you have a primary alcohol and you're trying to oxidize that up, and you got some other functional groups present, the other functional groups are not going to be affected by the Swern. So that's why it's so widely used. All right, so we're gonna stop here so I have time to make this link so I don't forget. But I'm gonna create a link today, and this is due today. I'm gonna give y'all all day though. I ain't gonna make it due like right after class. But it'll be up, but the link is gonna close like at 11:59 tonight. So you got between now and midnight to find this reaction, which it really should take you 10 seconds to find it. But find the reaction, look at the mechanism and how it happens. And I want you to turn it in today. You can just take a screenshot of it or print it as a PDF and upload it to Blackboard. All right, we're gonna stop here. And then we're going to pick this up on Wednesday. And I'm gonna send you some videos today. Also, let me start recording. I don't know if anybody